Hello everyone. In this video, we will be discussing some questions from the Math Olympiad. So let us have a look at the first one. So this one is saying that you have to prove that the cube of any positive integer greater than 1 can be written as the difference of squares of two numbers, two positive integers. So that means you are trying to say that be able to write n cube in this form. So now we can think it of in two cases. Case 1, if n is odd, then n cube is obviously odd. So we are getting a squared minus b squared is odd. So like let's take 2p plus 1. So that means when you split this as factorize it, a minus b times a plus b, which is that odd number, then we can conclude that both of these two, which are factors of that odd number. Why are they factors? Because a and b are integers. So a comma b are integers, right? So since both of them are integers, these are factors of that odd number. So both factors will be odd. So a plus b will be an odd number and a minus b will also be another odd number. So when we try to solve them, we add them, you'll get 2a equal to an even number, we'll get the value of a, and hence we'll also get the value of b. So you'll be able to express n cube in the form of a squared minus b squared if n is odd. Number two, if n is even, so that means n cube is obviously even, but it's a multiple of 4. It's a multiple of 8 to be precise. Right? Because if n has a multiple of 2 in it, then cubing it will become 8. But we are not interested in the 4 concept. So that means we are going to get a squared minus b squared to be 4k. A multiple of 4. So when we split a minus b times a plus b equal to that multiple of 4, we are going to do it in such a way that these both factors are even. We cannot keep an even and odd combination because then when we try solving, it will be not possible. So we write a minus b equal to an even number and a plus b to be another even number. And then when we add them, 2a will be an even number. So we'll get a value of a, hence get the value of b. That means irrespective of the scenario, even if n is even or if n is odd, we are going to be able to solve this. So we have been able to prove that it will always be possible to write it as a difference of two positive numbers. Let's go to the next question. Now this one is saying that if ABC are positive integers, show that it is impossible to have all of them to be perfect squares. Now here the point is that ABC are positive integers and we are trying to show that all three are not positive perfect squares. Okay, all three cannot be perfect squares. So if I try doing that, so what will happen to a squared plus b plus c? We are saying that this is a perfect square, right? Perfect square term. So that means obviously b and c are both positive. So that means a squared plus b plus c will be a square of something bigger than a, right? At least a plus 1 square. The next number, right? So from here what we get? That will give us similarly the same logic if I use for the others. And add them, I'm going to get on this side also twice of ABC, and on this side I'm going to get twice of ABC plus 3. Okay. Now, as I said, that this need not be a plus 1 square, it could be a plus 2 square. So this number can be greater than or equal to a plus 1 square. Okay. So actually what we are going to get is greater than equal to for all of them. So you end up getting 0 greater than or equal to 3, which is not possible. You cannot have 0 greater than or equal to 3. Hence, it is impossible to have all three perfect squares. Okay, let's go to the next question. Here we have to show that there is no natural number for which this is a multiple of 121. So let us say n squared plus 2n plus 12 is a multiple of 121. So we have here n plus 1 whole squared plus 11. So n plus 1 whole square to be n plus 1 whole square to be. Now since it's a square term and I have an 11 here, then I need another 11 as a factor somewhere. But this cannot be a multiple of 11 because 11m is a multiple and from there you have subtracted 1. So if you have subtracted 11, then you would have got another multiple of 11. Okay, so we subtract 1 consecutive numbers 11m and 11m minus 1. So this will not have a multiple of 11, hence this is not possible. Right, let's move on. Now here they have said that A, B, C are real numbers such that we have to check or we have to show that this fraction here will become an integer. Means you can basically simplify and you will get a whole number on top. So simplifying what we have is now here we deliberately add a squared. So we have 3a squared minus a squared minus b squared minus c squared. So now this a squared and b squared from here is basically 2c squared. So that becomes minus 2c squared minus c squared is minus 3c squared. We'll take the 3 out and factorize. And after factorizing, you see that a plus c as a factor cancels out. Now next step, we will multiply these two. We have a squared plus ab plus 2ac minus ac minus bc minus 2c squared. So now 2ac minus ac. So there is one ac left. And this 2c squared, we can write it as minus a squared minus b squared with a minus n in front. So 3 times. So now after this, from here on top, you can take out b common from the first and the last term. C is outside. And c common from the middle too. Finally, we end up with which is an integer. Okay, let's go to the next one. So you have to solve for this. So let's cross multiply. And then minus 1 you separately multiply. All right. Now this becomes, this goes that side. So it becomes m minus n squared plus 4mn, which is m plus n whole squared. So if I take out m plus n as a factor common, this side will have m minus n squared and this side will have m plus n. If I take this to that side and this side will have 0. Okay. So this is what we have. In fact, you can just drop the. Now from here, one thing we can say is m equal to negative n. That's one solution. So that means for every m, you have a negative n. So like m is 2 and n is negative 2, like that. One solution. Or this will be 0. Now for this portion, what we can do is we can define, let's say, m minus n to be some other variable, let us say a p. Then in that case, m plus n becomes, m is now n plus p plus n. So from here, we end up getting, so n will be p squared minus p divided by 2 and m will be this plus p, so p squared plus p divided by 2. That would be another solution. Define in terms of the difference. And just like we did for m and n, here instead of writing m minus n squared, it could also have been n minus m squared, depending on who is the bigger one of the two. So the values of m and n actually can swap, and you will get another solution, which is n equals p squared minus plus p over 2, and m equals p squared minus p over 2. So that would be the third solution. So we have got the three sets of solutions here. Let's go on to the next question. So to solve for this, now obviously x equal to 0 clearly satisfies. So we get 1 plus 1 plus 1 equal to 1 plus 1 plus 1. So 3 equal to 3. I have to check whether any other real solutions are possible or not. So if I define 2 raised to the power x as a and 3 raised to the power x as b, then all the other terms can be expressed in that. So 6 to the power x is the product of these two, because 2 to the power x times 3 to the power x will give you that. 9 to the power x will be square of b. Similarly, 4 to the power x will be square of a. So the equation that we have is this. Right? So this can be written as p plus a whole square minus 2ab. And now take these terms this side, minus ab minus p plus a. So we are going to get, in fact, this won't really help us much. Let us do it in a different approach. So this one can be written as b minus a whole square. Remember, b is bigger than a, right? But if x were negative, then a would be bigger than b. So it can go both ways again. So b minus a whole square. So that will get you b squared a square minus 2ab. So I need to add a ab. So that's can be factorized as a minus 1 times b minus 1. So now continuing here, this can be written as b minus 1 whole squared. B minus 1 minus a minus 1 whole squared. Like b minus a, I'm writing it like this. So this gives us minus 2 times the product, which is plus once the product. So it will be minus once of this. So now, if I were to replace this as b minus 1 is, let us say, something like um, m, and a minus 1 is something like n. So we have m squared minus mn plus n squared is 0. If I rewrite it in divided by n squared throughout, so m by n squared minus m over n plus 1 is 0. If I try to solve for the ratio m by n is how much? It is minus b squared minus 4ac over 2a, and which is not a real number, right? Because inside you have a negative number inside the third root over. So that means there is no other real solution other than x equal to 1, x equal to 0. Sorry. All right, let's go to the next question. We need to find the value of this. So you can clearly see, first of all, that this is basically the sum of these two. So there is a small typing mistake. This would be squared. Yeah. So now, if you look at the numerator, we can basically write it like this. Now, to avoid writing 2007 every time, we can just assume. So the question now is basically this divided by. So now we need to expand the thing on the top. Below you have, so here we have 1 and 1 two times, 2x to the power 4, 2x cube inside, 3x squared, and 2x. This one also 2 common, 1 plus x squared. So rearrange the terms on top. So it's 1 plus 2x plus 3x squared plus 2x cubed plus x to the power 4. Now this is actually, so now why is it so? If three terms ABC are squared, then you have a squared, then you have x squared. So if I, let's say, were to square that, let's see what we get. So this one will now become 1 plus x squared plus x to the power 4 plus 2ab plus 2 of these two and 2 times of these two. So we will end up with see 1, then 2x, then 3x squared, then 2x cubed, and x to the power 4. So this is clearly 1 plus x plus x squared. So since x was 2007, the answer is, let's go to the next question. We have to prove that 1 added to the product of 4 consecutive integers is a perfect square. Let's take the numbers to be this plus 1. Now let's multiply these two, multiply these two. So when you multiply these two, we get n squared plus 2n minus n. So plus n minus 2. And here n squared plus n. Take n squared plus n to be a. So that is a minus 1 whole square. And a is basically n squared plus n. So we have shown that 1 added to the 4 consecutive product is basically square of a term. Alright, let's go to the next one. So we have to compute this. So we can going in the same steps as the previous question. Let's multiply these two and these two. So if I multiply 31 with 28 and 30 with 29. So now this can be thought of to be 869 minus 1 times 869 plus 1. So the result is 869. Okay, let's go to the next question. So here it's saying that n plus 20 and n minus 21 are perfect squares. Okay, let's call that p squared, q squared. Now if I subtract them, since 41 is prime, the only combination possible is so in that case twice of p will be 42 if I add them. So p is 21 and q is 20. So that means n plus 20 will be 21 squared, which is 441. So 441 minus 20, so n is 421. So that is one solution. Okay. Like plus 20 if you do, you will get 441 and subtract 21, you will get 400. If I try doing the other way, that p plus q is 1 and p minus q is 41, then p will be 21 and q will be minus 20. The solution will remain the same because negative 20 squared is the same as 400. Okay, whether it's positive 20 or negative 20, it doesn't really matter. Similarly, if I try doing p plus q to be negative 41 and p minus q to be negative 1, then if I add them, we'll get p to be negative 21 and q to be negative 20. but the solutions are the same of n is the same because p squared values would not change. So there is only one solution, which is 421. Next, we have n squared plus 19n plus 91 to be a perfect square. So let's call that p squared. Let us solve for n. Okay. Now, if you try to complete the square on the left side, so it will be n squared plus 2 times n times 19 over 2. So now 19 squared is 361 by 2 square is 4. So that's 90 and then 1/4. But we need to make 91. So we have 3/4 left. Okay. So this becomes now n plus 19 over 2 whole square plus 3 by 4. Now, obviously, we are saying that n is an integer, so p and p is a perfect square, so that's also an integer. So if I have to keep all integers, and then 19 by 2 is coming out as a fraction. So let's simplify that part a little bit. So we write 2n plus 19 whole square divided by 4 plus 3 divided by 4 is p squared. Now multiply the 4 that side. So 2n plus 19 whole square plus 3 is 2p whole square. So what we have now is there's a square number plus 3 gives you a square number. So two squares having a gap of 3. Two squares with a gap of 3, only possibility is 1 plus 3 is 4. So here 2n minus plus 19 will be square will be 1. So 2n plus 19 is 1 or minus 1. So 2n would be 1 minus 19. So that's negative 18 or so n will be negative 9 or negative 10. Just to check with 10, for example. So n squared will now become 100. This is 91, 191 minus 190. So that's a perfect square. So that is fine. If I try with negative 9, then 81, 91. So that is 172. And 19 times 9, 171. So, so that's another one. So that is also square number. Okay. Uh, if I try with, yeah, so basically we have got negative 9 and negative 10 as the values of n. Okay, moving on to the next question. So here says that p and q are integers such that if this is divisible by 9, they must both be divisible by 3. So we have p squared plus pq plus q squared is equal to a multiple of 9. Now, they're all integers. Let's, in order to factorize, we add 1 on both sides. So that the left side now becomes p plus 1 times. No, sorry, that's p squared and q squared. My mistake. Yeah, so we have p squared plus q squared plus pq is a multiple of 9. So now let us say that you have to show that both are divisible by 3. Okay, so if I let's say show that p is a multiple of 3, but q is not a multiple of 3. Okay, means q is not a multiple. So that means p squared becomes a multiple of 9. Okay, pq is a multiple of 3. Multiple of 9 is also a multiple of 3. PQ is a multiple of 3 and 9m is obviously a multiple of 3. So in this equation we have this is a multiple of 3, this is a multiple of 3 and this is a multiple of 3. Hence it must be that q squared is a multiple of 3. But q squared, q is an integer, right? If you square it, you are saying it's a multiple of 3. Now if q squared was only 3, then cube becomes irrational. So q square is a multiple of 3, that must be a multiple of 9, and therefore q becomes a multiple of 9. So that means if one of the numbers p and q is divisible by 3, then the other one also has to be divisible by 3. Multiple of 3, not 9. Now next we will check if neither of them is a multiple of 3. Okay. So we have, so now if none of them is a multiple of 3, and this you are saying is a multiple of 9. So now if neither of them is a multiple of 3, first of all, this is a multiple of 3, this is a multiple of 3, so this must be a multiple of 3. Okay, if it's a multiple of 3 and squared it, it's a square, so it has to be a multiple of 9. So we have a multiple of 9, you have a multiple of 9, so this has to be a multiple of 9. But you only have a 3 here, means you must get a 3 from one of these. Therefore, one of these two must be a multiple of 3. And again, from there, you can conclude from here that if one of them is, then both of them must be a multiple of 3. And hence, we have the proof. Let's go to the next one. So how many of these have odd numbers as their tens digit? So if you look at squares, so you have numbers which end in 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. If I square them, so I've written 2, 1, it could actually be any even number. Let's keep E for even. And O for odd. So what we end up getting is the tens digit, which is going to have an odd digit, is only possible if the units digit is ending in 6, and thus everything else other than that would always have an even digit in the tens place. Now, this will become odd, therefore, when you have a number ending in 4, when you square it. So, for example, 4 squared, 16, 14 squared, 196, 24 squared is 576, and so on. Similarly, 6 squared, 36, 16 squared is 256, 26 squared is 676, right? Yeah. So now we have to basically figure out how many numbers end in 4 or 6 from this. So in every 10, so 1 to 10, and then 11, 20, and then 21, 30, and like that, if I keep doing it, I will have one number ending in 4 and one number ending in 6 with the units digit. Okay, we can do it like that and count how many such cases we'll get. So when we last stop, so we are going in groups of 10, and let us say this is like 2000. Okay, so how many such groups will we get? So 2000 numbers, 200 groups. Okay, that will give you the answer. Alternatively, we can just do a little bit of permutation combination. So we have single digit numbers, two of them, two digit numbers. If it ends in 2 or 4, so here we'll have 9 options. Here we'll have 9 options. So 18 of them. Three digit numbers, ending in 2, ending in 4. So here we'll have 9 options, here we'll have 10 options. So 90 and 90 again. So that makes 180. And finally, so here we have stopped at 999. So now from 1000 till 1999. So 1 is fixed. Here we'll have 10, 10, 100 options. And here again 100 options. So 200. So here we have 20 plus 180. So that's 200 plus 200. So such 400 numbers. Here also is the same thing. There are 200 such cycles and each cycle has 2 numbers. So 400 numbers are there. So that's the answer. All right, moving on. We need to calculate this value. So here we have a to the power 4 plus b to the power 4 plus a plus b whole to the power 4. Okay. So if I do the calculation, okay, so this will be the pattern. This whole thing divided by 2. So we'll have 2 times a to the power 4, then 4 a cube b. So 2 I have taken common. Then 3a squared b squared. Then 2ab cube. And then 2b to the power 4. So now this is basically a squared plus ab plus b squared whole squared. If you check, if I square this, then if I look at the square, a squared plus ab plus b squared whole squared will be this square, square of this, square of this, then 2 times this, then 2 times this, and then 2 times this. So that gives us a to the power 4 plus b to the power 4, then 2a cube b, then 2ab cube, and then 3a squared b squared. So that's what we have. So when we take out the square root, it's simply a squared plus ab plus b squared. So in this case, a is 11 squared. A is 11 basically. Then a times b is 11 times 100. Here we have a as 11 and b as 100. So the answer will be 121 plus 1100 plus. So that is going to be, sorry, and if we add 121 to that, so that will be 11221. So that is the answer. Let's go on. We have to show that this is not prime. That means we'll be able to factorize. All right, so let's say, so what we have is n squared minus, so 2 raised to 10 to the power 2014. So, okay, let's keep that for the time being. 4, this becomes now 2 to the power 4026. Or we can just keep it like, take out a 4, or we can keep it like this. Better is to keep it like this. So what we do is from here take out a 2 to the power 1 outside. So this also becomes 2 to the power 2013. And let's replace 2 raised to the power 2013 with a. So this equation now becomes n squared minus 2a times 2014 times n plus a squared times 2013 times 2015. So now you have to factorize this. Now this 2 times of this will become 4028an. Now clearly 4028 is the sum of these two, so we can factorize. So n common. Oh, sorry, this will be minus. So that means we have been able to factorize this whole thing like this. So once we have factorized this, we can therefore conclude that this is not prime. Okay? Another way of saying that none of them actually can be 1. Okay? If I replace that a, so what I'm going to get is n minus 2015 times 2 to the power 2013 and n minus 2013 times 2 to the power 2013. So we have clearly been able to factorize this in two parts, and hence we can conclude that this thing is not prime. Now we need to check that it does not lead to a case where this is 1 and this is a prime. Okay. Now the smaller of the two is one, this one. So if I take this to be 1, so let us say if that means n becomes, then the second term n minus 2013 times 2 to the power 2013 will become, from this 2015 times this, we'll subtract 2013 times this. So that is going to be 2 times 2 to the power 2013 plus 1. So that will be 2 to the power 2014 plus 1, which can be written as 2 to the power 1007 squared plus 1 squared, which can be thought of as, and then we'll subtract 2ab. So this is now the square of something, and this is 2 to the power 1008, which is 2 to the power 504 whole square. 1008 a squared minus b squared. So we'll have two factors for this. And therefore this is not prime. So that means if you have two factors, that's fine. But then one of the factors could have been 1 and then the other could have been prime. Even in that case, with 1 and this is not going to be a prime number. So that means you are always going to get a product of two or more prime factors. So hence it is not a prime number. Let's move on to the next one. So here let's cross multiply. So these two and these two. So here we'll have yz minus, all right. Now Okay, instead of cross multiplying, a better way of doing it, since we have to show that each of the fractions is that, so we'll write it as this: yz minus x squared minus x equals. Now we'll do subtract and go. Okay, we'll subtract them. So we will have uh, so here we have y minus x. So from these two we can take out y plus x times y minus x, and from these two we can take out z common. So we will have y minus x common, and we have x plus y plus. Okay, let's go to the next one. Okay, let's multiply out. So this one now simplifies to 4x squared minus 2x squared. Then the 4x comes the left side. So we have this. I have to figure out the factors for this one. So if I take out these three and take 4x common minus 4x common from these two, negative 4x. This can be factorized as x squared minus 1 times x squared plus 3. That will give us x to the power 4 plus 3x squared minus x squared, 2x squared minus 3. So x squared minus 1 goes common. So this will give us x squared minus 1, and this can be again factorized as x minus 3 times x minus 1. So x plus 1 times x minus 1 times x minus 1 times x minus 3. So the solutions are x equal to 1 or 3 or negative 1. Let's go to the next one. So you have to figure out all natural numbers n for which this is not prime. So this can be written as this minus, okay, n squared plus 2 whole square will be n to the power 4 plus 2 squared plus 2 times n squared. So we have to remove that. Now this is 4n squared. So difference of two squares. So now for this to be a prime, we need to have one of them to be prime and the other one is one of them to be 1 and the other one to be a prime number. The smaller of the two obviously is this one. So if I try for that, that will give you n equal to 1. And in that case, you'll get 5. So that means for n equal to 1, we are going to get a prime, but for everything else, it is not going to be prime. So the solution for n is all except n equal to 1. Everything except n equal to 1. All natural numbers except n equal to 1. All natural numbers except n equal to 1 is the answer. Let's go to the next one. So we have this equation. So take it that side. And so we have basically got b squared minus ab. Let's put it like that. B squared minus ab minus 13 is 0. So b squared minus ab is 13. And here b squared plus ab, plus a squared is 4. Now to check if there are any real solutions to this. So if I, let's say, divide them, so that gets us, that way what we'll get is a quadratic form of a square and b square. That's why we are dividing these. So 9b squared minus 4ab plus 13a squared is 0. Divide by a squared. Now for real roots, we need to have b squared. So in this case, like the coefficient of the x term, right? In this case, negative 4 squared minus 4 times the other two terms. This should have been greater than 0 or equal to 0. Unfortunately, this is clearly negative. It is not. It is actually less than. That means there are no real roots. Okay, let's go to the next question. All right, so we have been asked to solve these two. So let us do one thing. From here, the b squared value is, we'll substitute it here. Now, we can take the c squared and a that side. So a squared minus c squared is a minus b. So we need a plus c to be a minus b over a minus c. No, we need a minus b, b minus c, c minus a. Okay, so we'll keep a minus c instead. Yeah, sorry, this is a squared minus c squared is negative a minus b. Sorry, so we'll take out the negative sign common, a plus b will come. So a minus c will be minus of a plus b over a plus c. Adjusting the negative sign, we have finally c minus a to be a plus b over a plus c. So this one is a plus b by a plus c. Now using the same pattern, because these are cyclic relations, b minus c. So your c minus a started off with a. So c, it will be c plus. Now a and c are both present. So we bring in the other term. So b and c are both present. We bring in the other term. And then here the c, the first term is come. This will be c plus b. And finally here, it was minus a, started off with a. So it's minus b, it will start off with b. The upper term, a and c are there. So we bring in b. So here a and b are there. We bring in c. And here the c has come. So here the a will come. So the result will become a plus b will cancel, c plus a will cancel, b plus c will cancel, we'll have 1. Hence proved. Okay, so thank you for watching the video. I hope this was helpful. I'll be back with some more videos like this. Thanks.